I got distracted. I couldn't stop. Hey guys, sorry about that. I got a little bit distracted. The newspaper recently published the results of health inspections, restaurants nearby. My wife and I got curry from Bangkok Square the other day, and I'm sad to say that one of their locations is apparently in deep shit. Bangkok Square, I don't want to talk shit. They make amazing food, right? Really, really, really good Thai food. But this location, the Archer location, is apparently not doing a good job of taking care of roaches. So, whoops. Not at all relevant to Calc 2, but you know, just nonetheless. So you guys have done a good job soldiering through the first test. I have not graded those. The general rule for me is about 1 week turnaround time. So I'll be going by the testing center a little later today to recover the scratch work from the people who took it there. And then the rest of you who submitted your work online, I already have. So I'll begin grading those soon. Do not panic, right? If you look at your grading canvas right now for that test, it's just going to show the true, false, and multiple choice points. It's not going to show anything, right? Everybody right now has a 0 on all the free response problems until I go in and grade them manually. So since 60% of the test is free response, the maximum score somebody could have right now is 40. So don't panic if the grades don't look good at the moment. Nothing has been graded yet. All right, this is MAC2312, section 004, which means we're talking about Calc 2. And the date today is the 29th of September, 2021. Alrighty. The next kind of stop on this Calc 2 train is a gentle introduction to the notion of convergence. So the word converge, besides being a really good band from the 90s, the word converge basically means some infinite process leading to a finite result. It means some infinite process went well, things were good. And the opposite of converge is to diverge, which means some infinite process failing to work out well, maybe not leading to a finite result or something like that. So we're going to begin expanding our vocabulary, and the magic word is converge. The words converge and diverge will apply to many different things. The first things to which we will apply that vocabulary are certain kinds of integrals, and that's what we're going to talk about today. Specifically, these things called improper integrals. Today, we begin the middle third of the course by talking about improper integrals, and this is section 7.8. So it's a little jump there. After we talk about improper integrals, we're going to jump to chapter 11, 11.1, where we're going to talk about sequences. Sequences are a totally different family of objects, but we also have these notions of convergence and divergence. So the words converge and diverge we will apply to these improper integrals. Then we will apply them to sequences. Then we will apply them to series. And then with some qualifiers, we will apply them to special things called power series. So this is kind of the start of the hard part. The new vocabulary. The word converge. It's a verb, right? Something converges. It's a thing which is done. And this, in general terms, means infinite process yielding a finite result. The adjective form of the word is convergent. So this is an object which converges. And then going along with these, there's the new verb diverge. And this is an infinite process failing to lead to a finite result. And the adjective form of that word is divergent. And this is just an object which diverges. Okay, that's the vocabulary. And you want to use these words carefully, right? If there's one theme that you may have noticed in this class so far as you work the homework and other stuff, it's that you need to be like next level careful. One tiny fuck up anywhere in one of these big integrals screws the rest of the 3-page problem up. Never has that been more true than as we talk about convergence and divergence. We'll be dealing this time with integrals because those are the objects that we're most familiar with. We've messed around with integrals a lot this semester, but these terms are not native to integrals. In fact, if you're taking a graduate level real analysis class, you usually start by talking about sequences. You use sequences to build everything else up. And you could say that the word converge is kind of native to the study of sequences, but that's also, you know, slicing it too narrowly. So this is as generally as I can define these words for you. Converge is usually considered a positive result. If something converges or is convergent, then we're happy. And diverge is generally considered a negative result. If something diverges or is divergent, then we're disappointed. Not always, of course, there are books about divergent series. Ramanujan famously wrote one, but most of the time. Okay. The big question is how do I find all the area under a curve? Like not from x equals a to x equals b, but something like x equals a to x equals infinity. Or maybe even from negative infinity to infinity, right? Maybe that's what we would mean by all. So how do I find areas where the region isn't bounded? Turns out, and you may be surprised to learn this, such areas, such regions can have finite area. That is very possible. So maybe I have a curve that looks something like this. Y equals f of x. And I want to find all the area from A here all the way out. So rather than stopping at some finite number B, I want to ask, can I find all the area, you know, going on and on like this forever? Turns out if we want to, we can like write down some symbols that we think make sense for this. Like you would say integral a to infinity f of x dx, right? That's kind of what makes sense to us. You know, if I want the area from a to b under f of x, I integrate from a to b. If I want the area from a all the way out to the right, that means I'm going to do the integral from a to infinity. But we don't know what this means yet. So how on earth do you define such a thing? Well, it turns out you chop off at your favorite positive real number r. You find a formula for the area from x equals a up here to x equals r. I'll call that AR. That would be the integral from x equals a up to x equals r of f of x dx, right? And then, so we want this. And the way we get it is by thinking, okay, well, the total area would then be, if I can find a formula for this guy, I could then send r to infinity. So I find a formula for the area just up to r. And then I send r to infinity. i.e., and this is the definition, the integral from somewhere up to infinity of f of x dx is the limit, as I like to use capital R goes to infinity, integral from a up to r, f of x dx. So this is the object we're defining here is called a type 1 improper integral, and I'll go into all the details about how they're classified and stuff. But I just want to begin with this. This is something that I think has a lot of intuitive appeal. I want to discuss why these things require special treatment. They do, right? I can't just say I'm going to evaluate this with the tools we have, because the tools we have do not apply to this. Why, what sort of problems? So think about what your integrals and our integration theory is based on. It's based on Riemann sums. What sort of problems would you come up with trying to build a Riemann sum for this integral? So which we call improper, because the width of the region is infinite. I want you to think about this integral and channel your inner Calc 1 student. You remember back in section 5.1 when you were first starting to find areas under curves, and in order to do that, you had to build a Riemann sum. And then eventually we came up with integrals as limits of Riemann sums. What part of the Riemann sum process could you not do with this? Because the width of this region is infinite, that means delta x, which is normally b minus a over n, would be infinity minus a over n, which is definitely infinity. So we can't build a Riemann sum. And to you, that might not seem like a big deal, but it's actually a very big deal, because all of our integration theory is based on Riemann sums. Like when you do a definite integral, you find an antiderivative and then plug in the bounds, you're using Riemann sums. It's not something you're actively using. You're leaning on the fundamental theorem of calculus, part 2, which says that definite integrals can be found by antiderivatives and plugging in bounds. But that fundamental theorem of calculus is proved by using Riemann sums. So if you have an integral like this, where you can't build a Riemann sum because the delta x term would be infinity, you don't have the fundamental theorem of calculus. Okay, so kind of continuing this discussion. No Riemann sum means no fundamental theorem of calculus means can't do anything. Right? Means you can't evaluate the integral by finding an antiderivative. Means you can't do trig sub, you can't do u sub, you can't do integration by parts. None of it. Not even the most basic thing of saying like find an antiderivative and evaluate between bounds because you don't have the fundamental theorem of calculus. All of the integration work that we've done is built up around the fundamental theorem of calculus. The fundamental theorem of calculus is built up around Riemann sums. So if you don't have a Riemann sum, you can't do shit. Which is why we have this definition. You see, the integral on the left here is an improper integral because the delta x would be infinity, right? The width here is infinite. The integral on the right here inside this limit, this is a regular Riemann integral. R is, in this calculation, understood to be a fixed constant. And you find a formula for this integral in terms of that fixed constant r. Then you send r to infinity. So this first step of rewriting your integral a to infinity, as limit r to infinity, integral a to r, is a crucial step because without it, we can't do anything. This is why we define the integral a to infinity, the improper integral, the way we do. The integral a to r of f of x dx is a normal Riemann integral. So we can use our normal tricks on it. And that's what we want, of course. That's what we want. So you define the integral from wherever to infinity as the integral from wherever to r with a limit out front. Then you can apply all your normal tricks to the integral from wherever to r, because that is a regular normal Riemann integral. It's a finite width thing. Okay. So this is the basic idea, right? The kind of shocking thing here, in case it hasn't been driven home enough yet, the shocking thing here is that it's possible to have a two-dimensional region that's infinitely wide, but still has finite area. That's the big surprise. If you've never seen this before, then it can be a little bit shocking. Even if you have seen it before, it can be a little bit shocking. For us, the words converge and diverge in this context will mean that the total area measured by the integral is finite, right? Can be measured and is finite. So before I'll give you the technical definitions and all the names and stuff, but before I do that, I just want to look at a few problems and see if we can wrap our heads around what's going on. All right. So let's try to find all the area under f of x equals x over x squared plus 1, where x is greater than 0. I'd like to begin with a sketch of this graph. And drawing pictures in this section is still important. This graph, this is a famous function. It's called the Witch of Agnasi. With a lot of nice symmetries. Looks like this. So I'm trying to find all the area from x equals 0 all the way out to x equals infinity. The challenge, of course, is that infinity is not a real number, right? What we're saying is we want to just keep going. We know this area keeps going. I want all of it. The way we're going to do that is by integrating up to R, finding a formula for that area, and then sending R to infinity. All right, here we go. So the thing I'm after, I'll do it down here, is the integral from 0 to infinity of x over x squared plus 1 dx. And the way I'm going to get this, you must, for your first step, write this as a limit. Limit r to infinity integral 0 to r, x over x squared plus 1 dx. So the black integral here without the limit is the black shaded area here. And I think you would agree that as capital R goes to infinity, the black shaded area here becomes the pencil shaded area, which is, you know, all the area under this where x is greater than 0. The integral representing the pencil shaded area here is called an improper integral. It's improper because one of the bounds is infinite. So in order to get started, we have to write it as a limit of a proper integral. This is a regular, proper Riemann integral of the type we've dealt with all semester. How do I do this integral? Forget about the limit for a second. Just how do you do that integral?
U sub the bottom.
Very good. We need to substitute for the bottom. So I'll let u be x squared plus 1, which means du is 2x dx. So this x dx is 1/2 du. There will be a 1/2 coming out. I also need to change my bounds. And with these improper integrals, you need to be a little bit careful. So when x is equal to 0, u is equal to 0 squared plus 1, which is 1. When x is equal to r, u is equal to r squared plus 1. So make sure you change your bounds when you substitute here. Like we said, the differential term du, 1/2 du is x dx. So there will be a 1/2 coming out. I still have my lim r to infinity. Then 1/2 integral 1 to r squared plus 1 x dx was 1/2 du, and the other thing is just the x squared plus 1. So this is now 1 over u du. So I have here lim r to infinity 1/2. Let me get rid of the integral because we're going to take our antiderivative now. Antiderivative of 1 over u is the natural log of the absolute value of u. And I'm evaluating this between 1 and r squared plus 1. That gives me lim r to infinity 1/2 times the natural log of r squared plus 1 is positive, so we can get rid of the absolute values there, minus the natural log of 1, which is 0. So really what we have here, the 1/2 can come out past the limit. I have 1/2 limit r to infinity natural log of r squared plus 1. Does anybody know this limit? As r goes to infinity, what does this function do? Okay, forget about the log for a second. As r goes to infinity, what does r squared do? Just this piece. Yeah, that piece goes to infinity. So if you want to, in your brain, here's my advice. In your brain, replace the word infinity with really big number. If r is a really big number, then r squared is a really big number. And that means r squared plus 1 is a really big number. This is 1/2 times the natural log of infinity. Right, that's one way to say this. And then what does the natural log function do as its inside goes to infinity? What is the natural log of an enormous number? Oof. So the natural log function as its inside gets bigger and bigger also gets bigger and bigger. This is 1/2 times infinity itself, which is infinity. So the area under this curve everywhere to the right of 0 is infinite. This improper integral is infinity. So we say here, if I want to use that new language, since the value of the integral, the improper integral is infinity, we say the integral 0 to infinity x over x squared plus 1 dx diverges. That would be the way we would use the language here. So these limits at infinity, these are things you guys need to know. I am aware that not every Calc 1 class treats them with the love they deserve. You may want to go back to sections 2.6 and 4.4 in the Calc book and review some of this limit at infinity stuff. So limits at infinity are introduced in 2.6. And then section 4.4, I think, talks about limits at infinity again, because we talk about indeterminate forms and L'Hopital's rule. Those skills need to be here, right? This limit is something we should be able to cook up fairly quickly. So the pencil shaded area here, the area underneath this curve, everywhere to the right of 0 is infinity. And that's not too surprising, right? This region is infinitely wide. It goes on and on and on forever. The width is infinity. So we think, probably the area is infinity too. That's not too surprising, right? But what if I get rid of the x upstairs? Call the function g of x is 1 over x squared plus 1. And let's find all the area underneath that, where x is greater than 0. Is this function, in general, like for most x values, larger or smaller than f of x from the previous problem? If you plug in like x equals 10 to this, or you plug x equals 10 into x over x squared plus 1, which one would be bigger? Come on, guys, show me we're at least a little bit engaged here. What's bigger, this or this with an x upstairs?
That one.
So if I plug 10 in for x here, I get 1 over 101, right? 10 squared is 100. If I plug x equals 10 into the other guy, I get 10 over 101. 1 over 101, the output from this guy, is smaller than 10 over 101. This is considerably smaller than the previous guy. So the area I'm after here kind of looks similar, right? It's, it's an area, it goes on and on forever out to the right. Same sort of shit. But this function is outputting, in general, much smaller values. And we're going to come at it the same way. I chop at my favorite positive real number r here. I calculate the area from 0 to r, and then I will take the limit of that. So here, the integral from 0 to infinity of 1 over x squared plus 1 dx. I always begin by writing this as limit r to infinity, integral 0 to r, 1 over x squared plus 1 dx. And this limit is, this integral is a little easier than the last one. How do I do this integral? We just had a test on this stuff. What is the integral of 1 over x squared plus 1? Is there something in China?
Arctan.
Arctan, yeah, good. This is the arctangent integral. So this is limit r to infinity, inverse tangent of x, evaluated from 0 to r. No substitutions needed. So now I plug in my bounds, and I get lim r to infinity inverse tangent of r minus the inverse tangent of 0. And the inverse tangent of 0 is 0. What happens to the inverse tangent of r as r runs off to infinity? What is this limit? Very good, pi over 2. Here's what the inverse tangent function looks like. He has two horizontal asymptotes. One up here is pi over 2. The other one down here is negative pi over 2. Remember I said the graphs of inverse trig functions would be important, right? There's one place where it is. So the inverse tangent of r, as r goes to infinity, goes to pi over 2. So here we have an infinite process, right? This improper integral giving us a finite result. So all the area underneath 1 over x squared plus 1 to the right of 0, even though this is also an infinitely wide region, that area is finite. Finite, just a little bigger than 1.5. So since the integral has a finite value, we say the integral from 0 to infinity, 1 over x squared plus 1 dx converges. I'm going to graph those two. Well, this is the limit of the inverse tangent function, right? As the inside of arctan goes to infinity, the outside of arctan goes to pi over 2. It's coming from this graph, right? This is the graph y equals inverse tangent of x. So as the inside of the inverse tangent function goes towards positive infinity, the outputs get closer and closer to pi over 2. So again, you may want to review your limits, specifically your limits at infinity. Let's see what's happening in chat does most. So first, let's just attack that last question. Why pi over 2? As I put bigger and bigger and bigger numbers into the arctan function, which is what this limit is asking me to do, put bigger and bigger and bigger numbers, send r to infinity in the inverse tangent of r. Let's put bigger and bigger and bigger numbers in here. What does this thing get closer and closer to? Well, you notice these numbers, they're getting closer and closer to something. That something is pi over 2. This is coming from the graph for arctan, which we should all know has this horizontal asymptote. All right. So the function we got here for our antiderivative is the inverse tangent function. I had to plug in my bounds, and then I have this limit out front. So I got to take this limit, and that limit is pi over 2, which means that the area underneath this curve from 0 all the way out to infinity, you take all that area, it is pi over 2. And remember the way we're thinking of it. We're thinking of it as the limit of the area from 0 to r. So you find the area from 0 to r, that's the inverse tangent of r. And if you want all the area, you have to send r to infinity. Comparing the graph of the function that we were working with here, which is not this guy, right? He was just a tool for finding the limit. Comparing the graphs of the two functions we were just playing with, f of x equals x over x squared plus 1, and g of x equals 1 over x squared plus 1, you see this. The blue graph starts out bigger, but it gets smaller much, much faster. So the area we just calculated is this. Right, the area we just found is this purple area, all the way out to infinity. purple area was finite. The other area green here, the green area is the first area that we found. And you see how the green area is bigger than the purple area? Most of the purple area, from here onward, the purple area sits inside the green area. The green area is much bigger because that function is much taller, usually. The outputs from x over x squared plus 1 is bigger than 1 over x squared plus 1 by a factor of x. So the purple area was finite. The green area is infinite. Finite, infinite. Interesting, right? I get the feeling that we're having a little bit of trouble absorbing all the details here. Maybe it's because of the limit work or something else. So I want to take a second and just let you guys talk for a minute. What do we feel like? Is it just the limit work that's making this feel weird? Okay, well, let me show you one more example, one or two more examples where the limit work is perhaps a bit more straightforward. Here's two more improper integrals. We're going to do both of them. One is 1 over x squared. The other one is 1 over the square root of x. And both are being done from 1 to infinity. Again, I'm going to sketch the graphs for you. One over x squared has a piece over here. And a symmetric piece over here. And then maybe in green or something, I can put in the other guy. The other guy, let's see, he's going to start out down here. And do something like this. You might ask, how do I know which one sits on top and which one sits below? These are functions that I know well, but also x squared grows bigger faster than square root x. So the reciprocal of x squared will go down faster than the reciprocal of square root x. 1 is right here. If you plug 1 into 1 over x squared, you get 1 out. If you plug 1 into 1 over the square root of x, you get 1 out. So this is the point 1, comma 1. My scales are a little weird, that's okay. So the areas I'm looking for under the black function, it's all the area underneath him. Going on and on and on forever out like that. And of course, under the blue function, also going on and on forever like that. Looking at these, which one do you think is more likely to converge to give a finite value? The integral of the black function or the integral of the blue function? Thinking about what we said here, the purple area was finite, the green area was infinite. The purple integral converged, the green integral diverged. So here, what do we think is more likely to happen to the relationship between these? Which one is more likely to be finite, the blue or the black?
The black.
Good, the black is more likely to be finite because the black area is smaller than the blue area, right? The black area, the pencil shaded area, fits totally inside the blue area. So it's more likely that the smaller area will be finite, right? Both of them have this risk of being infinite because both are infinitely wide. But since the black is smaller, it's more likely that he's finite than the blue. Let's tuck that conjecture in our pocket and do the calculation. Yeah, very good. Frank and Coburn, correct, yes. All right, here we go. I want to do the integral from 1 to infinity of 1 over x squared dx. That means I'm going to write it as limit r to infinity, integral 1 to r, 1 over x squared dx. And 1 over x squared is a power function. That is limit r to infinity, integral 1 to r of x to the negative 2 dx, whose antiderivative is x to the negative 1 divided by negative 1. That's negative 1 over x. And we evaluate from 1 to r. I can't do the integral from 0 to r. I can't do the integral from 0 to infinity because both of these functions blow up at 0, right? That's why we're doing them from 1. And now if we plug in those bounds, I get lim r to infinity negative 1 over r minus negative 1 over 1, which is lim r to infinity 1 minus 1 over r. Okay, so what does 1 minus 1 over r do as r goes to infinity? Specifically the 1 over r piece. What does this piece do as r gets bigger and bigger and bigger? Yeah, what is 1 over infinity? Good, Prashant and Coburn, yes, 1 over r goes to 0. If you like, this is 1 minus 1 over infinity. And since 1 over infinity is 0, that's 1 minus 0, which is 1. This is a finite value. So we say that this integral converges. Well, let me practice the language. I can say it is convergent. Right? I could say that the integral converges. That's the verb. What's the integral doing? It's converging. Or I can describe the integral by saying it has the property of being a convergent integral. So like we thought, the black is finite. Does that automatically mean the blue is infinite? This is a deep question, so I want an actual response here. I want to hear what you guys think. The blue is certainly bigger than the black, right? The blue area is larger because the black area fits inside the blue area. The black area is finite. Does the fact that the blue is larger than the black automatically mean the blue is infinite? If I can shove a finite size thing inside of you, Are u necessarily infinite in size? No, no. Yeah, good, the correct answer there in the chat. All right, let's do the other calculation. I'll do it in this color. The integral from 1 to infinity of 1 over the square root of x dx. This is lim r to infinity, integral 1 to r. Always the first step, 1 over root x dx. And that 1 over root x, I can write as x to the negative 1/2. So this is integral 1 to r, x to the negative 1/2 dx, whose antiderivative can also be found through the power rule. You add 1 to negative 1/2, you get positive 1/2. So this is 2 times x to the positive 1/2, or 2 times the square root of x. And we're evaluating that from 1 to r, then taking the limit. So what we get out is limit r to infinity. 2 square roots of r minus 2 square roots of 1. And the square root of 1 is just 1. So this is lim r to infinity, 2 root r minus 2. Okay. What does the square root of r do as r goes to infinity? What's the square root of infinity? Anybody? To find this limit, you want to think about the graph of the square root function. Which you know looks like this. Yeah, it's infinity. As I walk further and further and further to the right along the graph of the square root function, my y values do go up to infinity eventually. So this is infinity minus 2, which is infinity. So this improper integral is divergent. You'd say the integral diverges, or is a divergent integral. Because the output, the result from that infinite process, is not finite. So our speculation was correct. The black area is finite, the blue area is infinite. Now that question I asked you can be evolved a little bit into a theorem called the comparison test for improper integrals. Before I state that theorem, which is the next thing we're going to do, I want to give you the proper rigorous definition of a type 1 improper integral. All right, definition. If f is continuous on the interval a to infinity, and we can define integral a to infinity f of x dx as the limit as r goes to infinity, integral a to r f of x dx, which is called a type 1 improper integral. We say the integral converges if the limit defining the integral, if lim, we say which integral, this integral, right, converges if lim r to infinity, integral a to r f of x dx both exists and is finite. Otherwise, we say the integral diverges. That is your specific and careful definition for a type 1 improper integral. All right, that's the term being defined here. Is type 1 improper integral. There is a type 2. Type 2s are where the region is infinitely tall. Type 1s are where the region is infinitely wide. So that limit has to exist and it has to be finite. It's possible for that limit to fail to exist. And it's also possible, as we've seen, for that integral to not be finite. We've seen a few examples, so let me go ahead and show you a couple of theorems. This is called the comparison test for type 1 integrals. If f and g are continuous on the interval a to infinity, and 0 is less than or equal to f of x is less than or equal to g of x, then if the integral from a to infinity of g of x dx converges, then the integral from a to infinity of f of x dx converges. And if the integral from a to infinity of f of x dx diverges, then the integral from a to infinity of g of x dx diverges. So I want to pause for a minute and just try to understand what this is saying. And then I will give us a little bit of practice. This inequality right here, this is the big thing. Remember when I asked you which function is bigger, which function is smaller? That was trying to establish a relationship like this. So if f is always smaller than g, the graph of g is always above the graph of f. So the area measured by this integral is larger than the area measured by this integral, because the function g is bigger than the function f. So if the area of the big guy is finite, then the area of the little guy has to be finite. In other words, what this first piece is saying is if you fit inside a finite box, you must be finite in size. Right? This area fits entirely inside this area. So if this area is finite, this area also has to be finite. If you fit inside a finite box, you are finite. The kind of flipped around version is if the small guy is infinite, then the big guy also has to be infinite in size. So if you fit in a finite box, you are finite. Okay. If an infinite box fits inside you, then you are infinite. That's what this theorem says. Okay, and the picture is like the pictures we've shown. I'll draw one more kind of general one here. Maybe this is F. This is G. Maybe A is here. So the purple area fits entirely inside the blue area. So if the blue area is finite, then the purple area has to be finite as well. And if the purple area is infinite, then the blue area has to be infinite as well. That's all. Okay, let's make use of this. And then I have one other theorem that I'd like to share with you, and then you'll be ready to work some of these problems on your own. All right, let me say one more thing, I'm sorry. This is our first convergence test. As this middle part of the semester wears on, we're going to develop convergence tests for integrals, convergence tests for sequences, convergence tests for series, and convergence tests for power series. You want to set aside several pages in your notes for convergence testing. Like grab 4 or 5 pages in your notes, set them aside. You're going to put convergence tests there. That way you'll have one place to go back and look at all your convergence tests. There will be several categories: convergence tests for integrals, convergence tests for sequences, convergence tests for series, and convergence tests for power series. We'll have several theorems within each of those categories. This is the very first one, and it is a convergence test for type 1 improper integrals. And again, what this really says is if the blue area is finite, then the purple area is finite. Oh, I should have used purple, sorry. And if purple is infinite, so is the blue. That's really what this theorem says. And it's by containment because the purple fits inside the blue. All right, one more theorem and some example problems. This next theorem has to do with a family of integrals. So I guess a definition and a theorem. Improper integrals of the form integral a to infinity 1 over x to the p dx, where a is positive, are called p integrals. So like the 1 over square root x and 1 over x squared integrals, those are p integrals. stuff of this form. Integral 1 to infinity 1 over x to the 2. That fits in this form. It has to be exactly this. If it has anything else, like other x stuff down here, x stuff up here, anything other than this, it's not a p integral. Only things of this form. And then the theorem. So, theorem, this is a next convergence test. We'll call it the p integral test. This says very simply that p integrals converge if p is strictly bigger than 1 and diverge if p is less than or equal to 1. And the proof of this theorem is not bad. So there's something special about 1 over x. 1 over x is kind of a tipping point. If you are a p function, if you like 1 over x to the p, and p is greater than 1, then the area underneath you from 1 to infinity or wherever is finite. And if p is less than or equal to 1, then the area under that curve is infinite. You have to split it up into cases. If p is equal to 1, then we have integral a to infinity 1 over x dx, which is the limit as r goes to infinity, integral a to r 1 over x dx, which is lim r to infinity, natural log absolute value of x evaluated from a to r, which is the limit as r goes to infinity of the natural log of r minus the natural log of a. And the natural log of r goes to infinity as r goes to infinity. So this is infinity minus the natural log of a. And since the natural log of a is necessary finite, this is infinite. So the integral diverges if p is equal to 1. If p is not equal to 1, then integral a to infinity 1 over x to the p dx is lim r to infinity integral a to r 1 over x to the p dx, which is done as a power rule thing. So that's x to the negative p. R x to the negative p dx, which is equal to lim r to infinity. If I add 1 to this power, negative p plus 1, that's 1 minus p. So this is 1 over 1 minus p times x to the 1 minus p, or 1 over x to the p minus 1, evaluated from a to r. If p is bigger than 1, then this power is positive, and this x really belongs downstairs. So I can pull out the 1 over 1 minus p. And what's left here is lim r to infinity 1 over r to the p minus 1 minus 1 over a to the p minus 1. And this limit right here lim r to infinity 1 over r to the p minus 1 has 2 possible values. If that term really belongs downstairs, if p minus 1 is a positive number, so this r to the p minus 1 really does belong downstairs, then this is going to be 1 over infinity, which is 0. And that's if p minus 1 is greater than 0. On the other hand, if p minus 1 is negative, then this term really belongs upstairs. This is like r to some power, right, upstairs. So that would give me infinity if p minus 1 is less than or equal to 0. Now I'm really just considering, I'm not interested in the case where p is equal to 1. I've already handled that separately. So this guy is 1 over 1 minus p times 0 minus 1 over a to the p minus 1 if p minus 1 is greater than 0, which is the same as saying p is bigger than 1, or 1 over 1 minus p times infinity minus 1 over a to the p minus 1, which would definitely be infinity if p minus 1 is less than or equal to 0, that is, if p is less than or equal to 1. And that's the proof. So we're gonna, I don't want you to stress too much about the proof here, but you certainly need to be comfortable with the result. So, this stuff here, we kind of tuck it into a box where we talk about the limit. This will be a continuation of that previous line. What page did we want to go back to there? The statement of the theorem. Or did we just want to see the start of this? I see. Okay. Let me hold here for a second because I'm sure people are still writing, and then I'll flip back to that. Okay, about 5 more seconds. The big deal here is that if p is equal to 1, the integral diverges. If p is not equal to 1, then there's 2 possible cases. Either p is bigger than 1 or p is smaller than 1. If p is bigger than 1, we get a finite value out. If p is smaller than 1, we get infinity out. So the important thing to remember here is that p integrals converge only when p is strictly bigger than 1. If p is less than or equal to 1, then they diverge. And that comparison term is here. So this says, if one function is always bigger than the other, and they're both continuous on the interval you're trying to integrate over, then if the big integral is finite, the small integral is also finite. And if the small integral is infinite, then the big integral is infinite. All right. So some things for you to think about. How am I doing on time here? I know I'm 1 minute over. I'm going to steal just a little bit more of your time. Let's talk about a couple of examples. Determine whether the integral of, actually, let me do it like this. This will feel a little weird. Whether the integrals converge or diverge. And I'll give you a few. We can do the integral from 1 to infinity of sine squared x over x squared dx. We can look at the integral of, let's see, how about the ln of x over the square root of x dx done from e to infinity. Yeah, let's do these. All right. So what I want to use here is my result on P integrals together with our comparison test. Those things work well together. P integrals form a nice basis for comparison. The kind of related P integral for each of these should be pretty clear. In part A, I would begin by saying, well, I know that the integral from 1 to infinity of 1 over x squared dx is a convergent P integral, because here P is equal to 2, which is bigger than 1. So this thing, the black integral here, is not a P integral, but I can compare it to this thing. And the purple integral here, this does fit that form. A is 1 and P is 2. This fits perfectly into that form of a P integral. And because of my theorem, I know that this is a convergent integral, right? P here is 2, 2 is bigger than 1. So this integral has a finite value. We actually calculated it earlier. This integral is 1. What else do I know? Can I compare this guy to this guy? Is one of these functions larger or smaller than the other? We know sine is always trapped between -1 and 1, which means sine squared, if you take stuff between -1 and 1 and you square it, you get stuff that lives between 0 and 1. Right? If you square a negative value there, it'll become positive. But if you square anything between -1 and 1, it will never get bigger than 1. Therefore, now if I divide everywhere here by x squared, we get sine squared x over x squared is less than or equal to 1 over x squared. This should remind you a little bit of squeeze theorem stuff from Calc 1. You're building inequalities, and we will be doing a lot of inequality building. I don't turn on cam here. We'll be doing a lot of inequality building, like a shitload of inequality work. Inequalities are going to be everything in the middle part of this course. So the black function here, sine squared x over x squared, we discover is smaller than 1 over x squared. And we know if I integrate 1 over x squared from 1 to infinity, the result is finite. I get that is a convergent integral. So this function is smaller than this function, and this integral is convergent. So what can we conclude? This is now a logic puzzle. If sine squared x over x squared is smaller than 1 over x squared, and the integral of 1 over x squared is finite, what can we say about the integral of sine squared x over x squared? By the comparison test for type 1 improper integrals, what is true? Good. The integral of sine squared x over x squared must also be finite. The integral from 1 to infinity, sine squared x over x squared dx converges also. What do you notice about this argument? It's mostly words. It's mostly me writing down words. It's mostly a logic game. I didn't calculate either integral here. I didn't calculate this and I didn't calculate this. But I was able to show using an inequality that this integral is smaller than this integral. And since I know this integral is finite, that tells me this integral has to be finite as well. As you write your solutions, as you work the next set of homework problems and all the homework that we're going to be doing until exam 2, you need to be writing out these words and you need to be practicing them. You need to be writing in full sentences and making sure you're communicating effectively and using good logic. This is what makes Calc 2 hard. This right here is why Calc 2 has the reputation it does, because the middle chunk of this class, which is the bulk of this class, is mostly about logic and language. Yes, there's calculation. Yes, it is a math class, but the bulk of this convergence stuff is logic stuff. And that means you need to be able to communicate effectively. It's not just about being able to come up with an answer. The answer here is that this integral converges. Here is your answer. But I didn't get it by calculating. I got it by comparing and applying some theorems. So this is something you need to practice. And I'll tell you right now, the best way to practice this shit, look around, see who's here. Y'all got your cams off, that's whatever. Look around, see who's here. Pick someone or use the Discord and talk about these fucking problems. See if other people agree that your logic is good. Try to make sure you understand steps like this, where we're working with inequalities. It's not obvious. It's not obvious. And it's not a skill that you learned in Calc 1. It's a skill you're supposed to learn in pre-calc and practice a bit in Calc 1. But most people shove it so far into the fucking rug that they just ignore it altogether, basically. Can't do that here. Okay. One more important thing. This inequality is true for all real numbers x. This inequality is not true for all real numbers x. This is only true if x is not equal to 0. If x is equal to 0, these objects are undefined. So you usually want to specify, and here I'm just going to say for all x greater than or equal to 1, because that's where I'm working. I'm working from 1 to infinity. So that's where I need this inequality to be true. But it's actually true for all x besides 0. Okay, let's try to solve part B here, and then I'm going to let you go. So in part B, when I look at that, I say, well, I know that the integral from 1 to infinity of 1 over the square root of x dx, or actually I can say integral from e to infinity, which is integral e to infinity 1 over x to the 1/2 dx, is a p integral. And it's a divergent p integral. Why? Well, because this thing fits that form of a p integral where p is 1/2. A happens to be e here, that doesn't matter. But p here is 1/2, which is less than or equal to 1. So if p is less than or equal to 1, p integrals diverge. But this is not the integral I'm working with. My integral has a natural log x term upstairs. So just like we did here, I need to somehow build an inequality involving my function and the function whose integral I know. Here, my function is ln x over the square root of x, and the function whose integral I know is 1 over root x. So I would begin with a statement about 1 over root x. Certainly, it's true that 1 over root x is greater than or equal to 0. And also less than or equal to 1 for all x, say greater than 0, definitely. Right? That's the domain of this function. And everywhere in its domain, this function, oh wait, no, only if x is bigger than 1. Yeah, sorry. So if you put a number in here, which is bigger than 1, its square root will be bigger than 1. So this is 1 over something bigger than 1, you get something less than 1. And if you then multiply through by, let's see, is this what I wanted to do? Yeah. If you multiply through by, oh, wait, hang on. So what sort of inequality am I trying to establish here? This is a divergent integral, right? So what I would like to show is that this integral is larger than this integral. So this might, let's see, how do I want to say this? Yeah, sorry. So you see this, and it's a teachable moment, right? Sometimes you set up an inequality that's true, but then you realize, oh, wait, what I'm trying to show, this isn't actually useful. I want to show that this thing is bigger than this thing. I know this thing is divergent, and if I'm able to show that my integral is larger than a divergent integral, it will be divergent. So what I should begin with is actually an inequality for the natural log. Just like here, I began with an inequality for sine, and then I was able to introduce the p part of the integral. So let me actually begin with the statement about the natural log. What sort of inequalities can I say are true for the natural log between e and infinity? Well, definitely 1 is less than or equal to the ln of x, and 0 is less than or equal to 1 for all x greater than or equal to e. So if you start writing down an inequality and then realize it's not useful, that's okay. It's not the end of the world. Just stop, think about what you're trying to do, and see if you can come up with another actually useful inequality. This is true, right? We know what the natural log function looks like. It looks like this. This right here is 1. This right here is e. This is the point e comma 1. So if x is bigger than e, then the ln of x is bigger than 1. That's what I actually need to use here. And now this, if I divide through by the square root of x, gives me 0 is less than or equal to 1 over the square root of x is less than or equal to the ln of x over the square root of x. And this is again true for all x greater than or equal to e. This bottom inequality is the one I'm going to use. So here I'm saying that my function, ln x over root x, is bigger than 1 over root x. So we can say thus, by the comparison theorem, comparison test for type 1 improper integrals, the integral e to infinity ln x over the square root of x dx must do what? Since ln x over root x is bigger than 1 over root x, and the integral from e to infinity of 1 over root x is divergent, what can I say about the integral of the bigger function? Must also be divergent, right? So here's the integral I know. I know that this integral is divergent, and I know that the function inside that divergent integral is smaller than my function. So the integral of my function must be bigger than the integral of 1 over root x. And since one integral of 1 over root x is infinite, this guy has to be infinite as well. In other words, we'd say this is divergent also. And that is your result here. So these can be a little tricky, right? These are are not as straightforward as the types of problems you're used to encountering in math classes, because they require, on the one hand, a little bit of creativity. You come up with your inequality. And on the other hand, good use of logic, right? You need to work well with that inequality, make sure you don't misstep and say something that's untrue, like trying to build an inequality with magic, just introducing a term and saying this is true. You need to make sure you know it's true, right? In this case, we know our inequality is true because the thing we started with, this, that the natural log of x is bigger than 1 anytime x is bigger than e. And of course, 1 is bigger than 0. I included the 0 on the left here because our theorem has a 0 there. The functions f and g need to be positive. Then we divided through everywhere by root x. That gave me the inequality that I can actually use, saying the function I'm trying to fuck with is bigger than this guy. The integral of this guy I know is divergent, therefore the integral of the bigger guy must also be divergent. Practice the logic, work hard on these problems, and discuss them. That's the biggest thing, talking about this stuff. You need to build up that vocabulary. It's very important that you get comfy with these words convergent and divergent. It's very important you get comfy with the logic words that surround them. Correct use of the terminology is going to be a meaningful thing. You can get into trouble with incorrect use of the terminology. So please practice these, write them out, talk about them. Don't just go through WebAssign and click converge or diverge until you get 100%. You need to understand this shit. This is the basis for all the stuff we're going to be doing moving forwards. If you don't spend the time here, you're going to hate sequences and series. If you do spend the time here waiting to working till you understand this, you're going to love sequences and series. It's going to be badass. It's going to blow your fucking mind. I promise. It's really good stuff. But you got to sink in the time here to get comfy. All right. Happy to work with you guys. Come by office hours or send me a Canvas message or show up in the Discord, whatever you want to do there. Happy to work with you as much as we can. Please work with each other also. That's it from me for today. I got to get running. I'll see you guys on Friday. Oh, shit, really?